morning to you all. It's a great pleasure for me to introduce Professor Suresh Menon from Georgia Tech here this morning. It's also a proud privilege for me because I think Professor Menon was there when I was a grad student there, so there's a long association there. Yeah. Well, I'm getting old myself. Yeah, so Professor Suresh Menon is a professor of the Daniel Guggenheim School of Aerospace Engineering at Georgia Tech. His a bachelor's degree in aerospace engineering in 1976 from the Indian Institute of Technology, Kanpur, and a master's in 1978 in aerospace engineering as well. He then went to University of Maryland to obtain his PhD in aerospace engineering in 1984. He joined Flow Industries, Kent, Washington, as a research scientist, and in 1988 became a senior scientist and program manager for the Computational Fluid Dynamics Group in Quest Integrated Incorporated, formerly also known as Flow Research. At Quest, Dr. Menon led research teams at various research projects such as the active control of combustion instability in ramjet engines, supersonic mixing studies, vertical takeoff and landing, aircraft fluid dynamics, and hypersonic re-entry problems. In 1992, he joined Georgia Institute of Technology as an associate professor and became a professor in 1997. Professor Menon is a world-renowned expert in large eddy simulation of turbulent reacting and non-reacting flows and has developed unique simulation capabilities to study pollutant formation, ozone depletion in high-altitude aircraft jet plumes, and combustion in gas turbine and ramjet engines. He has been and is currently a principal investigator for a wide range of research projects funded by NASA, Air Force, Office of Naval Research, and NSF. He has published and or presented over 350 papers. Professor Menon is a member of the AAA and a member of the American Physical Society and the American Society of Mechanical Engineers, the Combustion Institute, and the Sigma Xi. He is a peer reviewer of numerous archival journals, NASA, NSF, DoD, and DOE research proposals. His research includes large energy simulations of turbulent mixing and turbulent combustion in fundamental and canonical unit problems, subgrid modeling of combustion in premixed, partially premixed, and non-premixed highly turbulent flows, simulation of supersonic mixing and combustion in liquid-fueled rocket engines, solid propellant combustion, and nozzle erosion, multi-phase detonation and blast explosive modeling with and without inert and reactive metal particles, agent defeat simulations of dense clouds of nanoparticles or aerosols, and studies of supersonic combustion with and without plasma control of flame ignition and stability. As I've always said, Professor Suresh Menon, like all other speakers that we have had, does not require an introduction, but going through the profile motivates us. So that's the purpose of this introduction, Professor Menon. The floor is yours. Thanks.
Okay, thank you. Satya, thank you for the invitation, and I'm glad to be here. I think last time I came here was around 1992, so it's been a while. But I'm glad to see a lot of people here, and some of you from IIT Madras have been in my batch and graduated from my group. So what I was going to talk today and the next couple of days is something called computational combustion, and as opposed to combustion or combustion theory or anything, the word computation is the key aspect of what I'll be talking about. And I'm just showing you some examples of simulation results. These are all simulations. On the left hand side, this just says a GE SNECMA CFM56 combustor dual. I'll talk about the nature of this combustion in the last lecture because these are all spray combustion. But this is the engine that is in the Boeing 737 and mostly a lot of these planes that you're flying around. This is GE TAPS, this is just a double section, say, not the exact design, obviously the exact design is classified by these companies, but this is the engine that is in Boeing 777. And this is a new concept called the NASA lean direct injection. Again, these are spray combustion systems, and so I'll be talking about spray combustion only in the last lecture. So I just wanted to show you these are kind of the large scale type of simulations that you have to be able to do, and these are all large eddy simulation results, and we'll talk about some of these challenges for this later on. So I don't know how far I will go in terms of how fast I speak. I speak a little fast, so you may have to catch up. The slides are available in PowerPoint, there are embedded videos, and there's a lot of information on my website. I'll inform that. So, but in lecture 1 and lecture 2 today, I'm basically giving you some background of computational strategies and challenges and what goes wrong and what goes right and what nothing works, and sometimes where you're making fundamental mistakes that you assume are correct. So I hope that these lectures and the first 2 lectures are useful from how to model, what kind of codes to use, why do you want to do it in the first place, and what will you learn if you did it. So I'll talk about a lot of these things, and I want to emphasize computational combustion contains fluid mechanics, obviously, or turbulence to be more precise. So combustion modeling cannot be done if you don't do turbulence modeling. So you have to know turbulence and how to deal with turbulence before you can tackle combustion on top of that. So both of them play together in a strange way. So just to give you brief history, I guess combustion is not new, obviously. That is how civilization began according to history books. And it was actually an active control of fire that started the business. Like people were able to not only use the fire but actually control it and for cooking and other purposes. And the record, sometimes more recently people are saying it is up to 3 million years ago, but the data suggests it's been done for a long time. And it comes from, and the civilization has grown from fires, as everybody knows, for good or bad. Our interest obviously is transportation systems, but the transportation systems can have double sides because you can transport people and other things. And there are nothing new in that sense. That is why sometimes combustion is considered an old field. It's been there for a long time and it's still around, and control of combustion still remains the driving mechanism, because all the combustion systems we are dealing with are in some respect control of combustion. And I just wanted to highlight that in all aspects of area combustion plays a role, and maybe somebody else has shown that. These are some cartoons of places, including climate and pollution, as we well know, and including things like in entertainment, and in combustion at the other extreme, which is uncontrolled combustion, or detonations, which are also part of combustion physics. So I will not be touching on all of these, but I just want to point out that the physics of turbulent combustion is inherent in all of these problems, and that's how we have to look at it. The other aspect, which has been talked about a lot in literature and papers and news, that maybe we can get rid of fossil fuels and reduce climate problems. And there's a climate meeting in Paris. You want to cut back on fossil fuels. The potential for that is there, but in reality, what it is for propulsion, fossil fuels are still the driving mechanism, and they are estimated to be around be the key way of propulsion or transportation. Maybe in industrial or residential there might be reduction, but transportation, as it increases, fossil fuels shall remain there. So and 97% of the transportation energy comes from gasolines and diesels and gas turbines, which is my focus in here. And as gas turbines become more and more efficient, their use will increase, not decrease, at the price of perhaps coal, which is dirty. So gas turbines becoming a serious driver for energy transfer for a long time. So I will not talk a lot about gasoline or diesel engines, except to mention there are some inherent similarities, because there are a lot of differences between gas turbines and ground transportation. So one point, like I mentioned, combustion is here, there, it's going to be around. So what can you do about it? I mean, well, the obvious statements are, let's make it efficient, let's make it low emission or zero emission. Well, that's not ever going to happen. Let's make it climate neutral. That may not also happen, but we can combine these three things and find the minimal operating condition perhaps, and that might be a valid way of proceeding towards the next generation designs. And that implies you are designing new devices, not learning about the old. The old is already on the table, so that's the challenge. The other point was that alternate fuel systems are available, maybe solar and wind may be around, but they also use gas turbines, and you also need gas turbine type propulsion energy systems when there is no solar or no wind, like a cloudy day. And so the idea would be that can we use just experiments to understand things? The answer is no, because experimental devices are very simple, as you may have seen in the lab. The real combustion systems are very complicated, so usually the experiment, that means is that you actually build the real thing, you test it, you retest it, and finally you think it is working. But a lot of times the system is not understood. Nobody knows what's going on inside. The laboratory or lab facilities are very different from the flight facilities, and then the question then comes is that can we use modeling to help that system, the design cycle? Because if we build it and test it and then learn from it, that's fine, but then after you learn from it, can you build a new one without testing and building it first? That's the question, because if you cannot do the predictive modeling, there is no point in some sense to just understand what has already been built and is already working. So that's the challenge of modeling computational combustion that we want to look at. So here are some combustion systems of interest, obviously gas turbine systems, and I'll be talking about premixed and spray systems, and because there are subtleties of similarities and differences. Internal combustion engines, which are also spray systems, but slightly different operating approaches. And then there are micro combustors. I don't know anybody's working here, but there are combustors being designed the size of a credit card that provide power, like body power or runs on cigarette fluid, lighter fluid. Obviously high-speed systems, which are scramjets, which are originally it was designed to be hydrogen, but now nobody's interested in hydrogen. It's all liquid-fueled hydrocarbon scramjets. Then obviously rocket engines, which are liquid oxygen, liquid methane. These are supercritical systems, very high pressure, which operate very differently. The other extreme is solid fuel rocket motors, which are condensed phase material that burns and provides thrust. And then there are things that are like fires, pulse detonation engines, deflagration to detonation transition. These are all combustion systems in some sense. And the question is that are they all that different? Obviously all it has is turbulence, it has fuel, you burn, you produce heat, and somehow you get power out of it. So in theory, they're all the same. It's the subtleties of the differences is what is interesting to understand, because sometimes that is the difficult part to separate, because sometimes when you focus on one thing, you optimize for that problem, and the moment you change it to a slight change to another system, everything falls down. You have to start over again, and that's something I'll talk about as we go forward. Other aspects, given the designs that are existing, and let's say you can even improve the designs. If you are familiar with car engines or aircraft engines, they don't make new changes. They make only small changes. That's because they can understand those small changes based on existing systems, but they won't change the entire system. They won't change from a 4-cylinder to a 1-cylinder that has multiple sub-valve system or something, because that requires a lot of research, a lot of development. So that remains a primary approach in the generation and advancements of design currently, but modeling could allow you to go to new designs, and that's the advantage of computational modeling. The other aspect which has become very new recently is the alternate fuels, because they're saying, okay, there are alternate fuels like oil sand, shale oil, biodiesels, biofuels left over from rice crops, and synthetic fuels where coal is dirty. If you can convert it to CO and hydrogen and stop the pollution at the source, perhaps this will be more efficient. But then the point becomes is that can we use them in the old systems? That means you just change the fuel and let's say everything works. The answer is very mixed right now. You can't just use the same fuel on the old system and get the same performance. So there are other designs also, for example, ultra lean and very high pressure combustor designs for the 787 and the next generation engines. The gas turbines are going to operate at such a high pressure that the liquid will change, phase change into vapor without a liquid transformation. The surface tension goes to 0. It's called supercritical combustion, which is typically in rocket motors, but now it's coming into gas turbines, and that's a very challenging aspect. I'll mention about that. And so the retrofitting the past designs with new fuels and new design, just like changing one piece and saying hope everything works, has turned out to be sometimes dangerous, sometimes it has actually blown up. And so I will talk a little bit about what are the challenges for that. So I'll talk a little bit more about lean combustion, and everybody knows when you do lean it is efficient because you use less fuel, get a better mileage, produce less NOx because temperatures are low, and lots of good stuff. But the interest aspect sometimes is the lean combustion is for idle systems for gas turbines that I will talk about. And then there is issues about stable combustion. Like that means, and it's a misnomer because I'll mention that later on, that turbulent combustion is always unstable. There's nothing like a steady combustion system, But when we talk about instability, that is a special aspect of turbulent combustion that becomes important, that you change things without having instability, And when you go to very high pressures, the main design criteria is that at a high pressure you can make the combustor tinier and tinier and tinier. That means the engine can become smaller and smaller, and so it has advantages from that purpose, but it has the price of very high temperatures. So not only supercritical combustion, metals cannot handle that. You have heat transfer problems which become much more serious. Current design transition challenges are in these 4 or 5 areas, something called lean blowout. As you go lean, as you know, eventually the flame can blow out. But do you know when it will blow out and why is it blowing out? And can you make sure that you don't reach that point to blow out? And those are the questions you want to know about lean blowout. Then ignition, of course, is always a problem, but for aircraft flying in high altitude, altitude relight is a very critical important point. Something engine blows out for some reason in altitude, you have to relight it. So that is usually at high altitude, it's low pressure, low temperature of air coming in, the combustor is hot, and you have to be able to inject fuel, vaporize, mix and ignite very quickly in altitude. The other alternate is cold start. Like you're sitting in the tarmac for a long time, the engine is cold, air is not that hot, cold, but it's room temperature, and the fuel is cold. So how do you start up an engine? How quickly do you start up an engine? These are all issues that become practical when you're changing fuels and changing operating conditions. And then of course combustion instability is a major issue. You may have, Sujit here does a lot of work in that area, extinction, reignition. And for scramjet type systems is what we call engine unstart, where you can actually swallow the shock into the combustor and just block the mass flow rate, and the engine will stop working at Mach 8, and that's not a good sign, So you want to try to understand these mechanisms, and as you can see from the wording, these are all unsteady transient problems. These are not steady state problems. There's nothing steady state about these things. Another aspect is what is it? What are the systems of interest, premixed or non-premixed? Well, there are good, bad, and ugly for all of them. I mean, typically premixed systems requires premixing. That means you have to mix the fuel and air. If it's a liquid fuel, you have to vaporize it and then mix it, obviously. And typically that is obviously that's the fuel air mixture. That's like a explosive thing. A spark will blow the whole thing up. So that's dangerous from that perspective. Typically it's used only in land-based gas turbines because you can do protections and backups and safety margins, and it's a size and it requires the size of the system can be larger. One of the obvious problem is once it's lit, you can't shut it down. It's going to burn right into the fuel, and typical things like flashback, detonation, combustion instability is well known for premixed systems. On the other hand, it can burn very lean, very efficient, very low emissions. So gas power generation systems are primarily what we would call a premixed system, although as I'll mention, there is nothing like a real premixed system. On the alternate side, non-premixed system, if it is gaseous system, it is not really, you can have non-premixed gaseous systems where you inject fuel and air separately and burn, but most of them are liquid fueled because liquid is dense and you can, storage is easier and compact volume, and most flight systems, all flight systems are liquid, most transportation systems are liquid in some sense. And again, in all of them, turbulence is playing a role, and how it plays a role is important. The point. So the non-premixed systems are generally safer. Obviously, can be turned on and off. They're less cleaner, and there are some emission issues. So one issue about power generation, I just want to highlight this as a key driver because this is a big driver for GE and Pratt, big companies, power generation companies. This black line is the CO emission as a function of equivalence ratio, and it shows that as you reduce the equivalence ratio, it's running lean. All power generation premix systems run lean. Typically they operate around point here, let's say just arbitrary. This one combustor picture is actually an experimental data. If you go from 0.53 or 0.54, you can see as you go down, the CO emission drops up to a point and then starts to rapidly increase. As you approach the lean flammability limit, you get a lot of unsteadiness. Sometimes what you happen is a local extinction occurs and you get a lot of unburned hydrocarbons being produced, which essentially can result in soot, but also unburnt material. And you can see that the change occurs very rapidly. So the challenge always has been that, so if you are here, if you operate at 0.45, everything is great. Your ppm levels are down to 1 or 2 ppm. You're breaking all records. And I mean, you might think 8 to 1 ppm is not what a big deal, but you're talking about gas turbines that are running forever, and I'll mention that in a minute. But the problem is that they don't know how far to go. So they always run on the rich side of the lean system to keep it stable, because they don't want the flame to go out. They don't want to have, in this scenario you can actually have extinction also, blowout also. This is the lean blowout limit also. So interestingly, these gas turbines use up tons of natural gas in an hour. So going from here to here, it is not only good for reducing emission, you reduce an enormous amount of fuel that is used. So from an engine company perspective, that's profit. You use less fuel. So their interest in designing may be less on the emission side than to make money, because they can go leaner and save more money. That's one of the prime motives. The other aspect of this thing is that I don't know about here, but in Greenville or where in Georgia Tech area, power generation is by gas turbines, and the gas turbine, typically a power generation region has 8 or 9 gas turbines sitting there. And if you're only using, it's nice weather, nobody's using air conditioning, all the gas turbines have to be always on. You never shut down a gas turbine till it comes from maintenance. It could be 10 years, could be 5 years, Till then it is always on, because it is called power on demand. When you turn on the switch, you must get power. So if every people in a state turn on the switch, the gas turbines have to ramp up to full power, and the full power operation might be somewhere down here. This is not the operating point, it might be up here. And so the power on demand requires that the gas turbines are always idling. So when power is not needed, and if naturally maybe only one gas turbine is needed, the other 7 are idling, but they're idling at this stage, because they don't know, they would rather idle here and maybe for months or half a year at a time, because a cold gas turbine, power generation gas turbine can take days to start up. Even a hot one can take a while to start up to spool up to full power. So these are all practical scenarios that people realize that as you put more and more gas turbines for power generation, these challenges become more and more severe. From a design perspective, for example, what goes on right here? What's the difference between operating here and operating here? Can you predict this point without knowing anything about it? And so these are, so improving ideal performance, that's why I call idle lean performance. Idling is actually a bigger challenge for gas power generation, gas turbines, than for flight systems. On the other hand, there are now battle tanks that use liquid fuel gas turbines, like the American M1 tanks. Typically, they are called. The old one used to give 8 gallons to a mile. It's not 8 miles to a gallon, 8 gallons to a mile. And the reason is that once you turn on those engines, they don't turn it off till the war is over. Because you want to move, you better have the engine on. So the system sits there and idles, and you have to keep refilling it, even if you're not going anywhere. Now it's obviously improved, in maybe it's 1 gallon to a mile, but the point is that even when you idle the system, the idle performance can be very bad, as opposed to what you might think about cruise. Cruise actually is a solved problem. There's not much going on there. It is the idle and full power where the problems are, and so there are areas that we want to focus on. Now, I'm not talking about internal combustion or diesel engines, because there are obviously some other aspects to it, and they have different challenges too. For example, gasoline engines typically uses lower hydrocarbon liquid fuels, because the gasoline is more refined, so it's actually running relatively rich, so it produces more CO2, which is bad. It requires fuel air mixing and spark ignition, which is also bad, because you can have problems. It produces NOx, CO, and maybe not that much soot emission, but the problem is more CO2, which is bad for climate. So which is why diesels became popular, because diesels use higher hydrocarbons, liquid fuels, which are less refined, but as a price, it contains more sulfur and nitrogen, also in the fuel itself, not let alone in the air, but it can burn at very high pressures and relatively lean combustion, so it produces less CO2, which is good. But on the other hand, it has an auto ignition problem, and it produces more soot and NOx, and sometimes some SOx, sulfur oxides, which are bad for other pollution and health, and soot is definitely bad for health, but SOx can affect atmosphere through sulfuric acid formation in the upper atmosphere. So as you may have heard, they were talking about shutting down, having more diesels because of less CO2, but till you can solve some of the other problems, even diesels have problems that are not observed. Now, gas turbines may have different issues, but there are some similarities between them. So finally, to get back to some of the relevance point, like I said, there are many types of systems. They actually can range from 1 centimeter devices to 10-meter devices. So it is the same fuel air, like let's say using methane air in all of the system, or kerosene or whatever, but it produces very different performance, power. How can it be? How can the same fuel, which has the same energy content, and produce different power generation? Is it just volume, or is it something else? One of the challenging answer is that no, it is turbulent combustion that is the key. Turbulent mixing can enhance combustion, and depending on the turbulence, you can get a lot of benefits. Obviously, there are some difficulties also. One of the challenges to understand is that the sum of the two, turbulence is bad enough, but turbulent combustion is not just the sum of the two. When you combine them, some new things happen. And so the goal of our work has been to try to look at modeling to look at these new designs. So the question is, what is the new design? Is it more of the same? The answer is that not really. If it is more of the same, then the companies are going to keep doing the same work. They have no incentive to change, because the market is not going to ask them to change. So question is, can we go to the edge systems? When I say edge systems, that operate at the absolute lean limit, or operate with very little fuel, or operate with very widely fuel flexible systems. So the problems now is that, and the new designs, if they start operating now, you'll have instability blowout. So the answer here is very simple: don't go there. Just don't do it. Stay away from the system. But if you really want to do the right thing, you need to go there and have to learn how to operate at that edge system. And you cannot test it at that system, because combustion instability means your rig in the lab will blow up, so you can't do that. But in the computer, we can blow up all the time, and in fact, we do that all the time, so not for the right reason either, so the point is that you can then use modeling in some aspects to bring in information to understand the physics of what's going on and then try to help in the design cycle, and and the question is how far can we go there. So I just wanted to point out that turbulence is essential, and even though this is computational combustion, I'll spend quite a little bit of time on the turbulence aspects, or at least some of it. It's not a solved problem. I teach turbulence and I tell them there's the only unsolved problem. Everything I'm teaching is wrong, or it's a hypothesis. There's nothing. Nobody knows what's going on, and yet we want to use it. We are using it, and we are controlling it. We are applying it, and we are succeeding in it. So obviously something must be there and that we understand without knowing everything. The question is, can we take that and add it to combustion and look at the combination of the things? So, but we need to know that the turbulence remains the guiding principle. Now, one other important aspect, if you have taken already any course in turbulence, you know that it is always unsteady, it's fluctuations, and it's essentially 3D. You have the classical vortex stretching effect. You cannot get turbulence formation at the small scales unless you have vortex stretching, which is typically a three-dimensional problem. So by that token, anything that is done 2D and steady state is really not real. It's maybe you can do something, so you have to understand the limitation of steady state analysis. Even in 3D, but 2D itself has an issue. So models that are developed just to improve 2D steady state, by definition, are not going to ever understand the real unsteady 3D parts of the turbulence, because you can't build in that information because it's a dynamical system. Turbulent combustion is also always unsteady and three-dimensional because turbulence is controlling the flame structure. So maybe laminar flames you can study in 2D or steady state, which makes sense. Once you bring in turbulence, it is going to become unsteady and three-dimensional. Now, I want to emphasize, when I say unsteady, it is not unstable. You can have fluctuations, but they are within a certain bound. Everything is fine. You can live with it. Unstable for combustion people are different from unstable for full turbulence people. And unstable combustion is when you have something called combustion instability, and that is something I'll talk about a little bit later. Then on top of that, combustion has chemical kinetics. I mean, everybody knows that no reactions are one step. Everybody uses one step. You have to use multi-step. If you have multi-step reactions, you have radicals forming that are very fast. So that means it's a very short time. It is a very high frequency, very tiny time scales involved. Now, if you ignore those time scales, one could ask, why bother with those species? If you're not seeing that time, why worry about a radical like CHO? Because it doesn't, you can't track it. But what if CHO is the controlling species for a combustion system? Then you have to take care of it. So it is becoming more and more clear that chemical kinetics must be taken into account in turbulent combustion modeling. If you really want to do design type problems. So it brings in an additional time scale that we don't know anything about, and that we need to go towards. And then obviously, once you bring in liquids, you have spray, droplets, and a few other good stuff that we will have to worry about. So turbulence, numerical, I will go run through a few aspects because typically there are various approaches. Everybody knows about Rand's approaches. Basically, you do time averaging and solve the steady state equations. Sometimes you do U-Rands where you do the unsteady equations, but that's really oxymoron because you've already taken out the time. So what's the time involved? What is the time about? Obviously, the extreme best scenario would be direct simulations where you resolve everything in 3D and there's no modeling. Obviously, that ends up becoming so expensive that typically it is low Reynolds numbers and small canonical problems. It is typically used in research type problems, very little use of DNS in any practical system. The area of interest here is more and then there are other aspects I'll mention about acoustics in a minute, but is what I call large eddy simulations or very large eddy simulation, VLES, which essentially are transient and three-dimensional. They resolve some scales of turbulence, and what they cannot resolve they model, but how they model is the challenge, because the modeling aspects have control all of the things. And the advantage of why this is a compromise is that it captures all the large energy containing scales in the simulation directly. You're not modeling it, you're getting it from the simulation, and if your model is right, your code is right, it's okay. You're only modeling the small scales where Kolmogorov theory or turbulence people have given us some idea what's going on there. So we can use that knowledge to build in subgrid models for this large eddy simulation, and I'll give you some examples. So, and then the various transition hybrid methods, which are all mixes of two. One way to look at it, and if this is a typical chart line, if capital L is the size of the device, which can be the size of a combustor or a pipe or whatever, and eta is the Kolmogorov scale, that by definition is the smallest eddy below which turbulence cannot exist. Dissipation kills all turbulence. Then L is typically what we call the integral length scale, which is type of scale where the large scale, the energy containing scales are. Then everybody knows that the range between L and eta, there is something called the inertial subrange where the energy cascades to small scales without dissipation, because dissipation only occurs at the small scales. So production of energy is here, dissipation is here, the inertial range is a dynamical self-similar region, and it increases with Reynolds number. Higher the Reynolds number, it goes with the power of 3/4. So so the idea here with DNS obviously is to resolve everything. RANS by definition is only doing the large scale because it has to model all the scales. Very large eddy simulation and large eddy simulations differ in two aspects. One, large eddy simulation stops somewhere in the inertial range. Where it stops depends on the cost issue. For example, if you go close to the dissipation range somewhere down here, then you have to resolve all of that. So the cost, just like in DNS, the cost goes up. If you go towards the right, towards the energy scales, then the cost is less, but then you have to model the inertial range, which has a price to pay. The very large eddy simulation stops somewhere here. It only captures a few of the large scales, and obviously have to model all of them. So the cost increases rapidly because as everybody knows, grid resolution goes as for Reynolds, DNS goes as Reynolds to the power 9/4. That means a Reynolds number of 10,000 will need 1 billion grid points, and typical Reynolds numbers we are talking about 1 million. So 10,000 is nowhere near the picture, And time step requirement go by a factor or even larger. So the simulation of a real system is longer than the universe has existed. So it is not possible to do simulations of real systems for any practical purpose. So the idea of LES then becomes is, can we move closer to the right so that the cost is reasonable and yet predict the physics of turbulence if this physics is ready. Notice that droplets are in this range. Droplets are 10 to 100 microns or 1 micron. They are always in the small scales. Keep that in mind. And combustion is occurring at the molecular scale. It's not even in the chart. So the question now you have to ask is that how can combustion affect this turbulence which is up here, because all turbulence is dead out here. But combustion is occurring here, but somehow it's feeding back and affecting turbulence, and turbulence is affecting combustion. So that's the challenge. They seem to be so far apart that you shouldn't care, but it does affect, and that's the point. One quick answer, like a PhD oral question, is that viscosity, temperature goes up, viscosity goes up, this point starts to move in, the flame turbulence effects start to feed back because of heat release. But then there are things what we call backscatter, because you have heat release fluctuations of the scales that feed back into the inertial range, and they counter effect the forward scatter effect. The forward scatter is energy going from large to small. So you want combustion can feed back into the large scales. So this is what I just said this in words, but I'll just leave you with a picture that in the end the gas turbine might be that big, but all we are doing is just looking at something that is maybe 10 centimeters to maybe 1 meter in a 10 meter power generation gas turbine. The combustor is only this big, actual combustor. In aircraft engines, the combustors are this big. Maybe it's annular, but in lengthwise it's not that big. In there you have to mix the scale droplets, mix it at scales that go from 1 centimeter to 1 millimeter, and molecular processes that occur at fractions of nanometers. So this is the range of scales that interact. So is that all in combustion? Well, answer is no, because fluid mechanics again plays a different role. If you've seen large scale vortex shedding, many of you may have seen that in fluid mechanics. If you look at the shedding frequencies, you find that it's Strouhal number. Based on Strouhal number, the typical time scales are 1 to a fraction millisecond of shedding, and the jet preferred mode are within that range also. You can see the numbers are overlapping. If you look at the typical devices that we are looking at, the acoustic longitudinal modes of acoustics, and this has got nothing to do with combustion, just noise, pressure modes, are about the same time scales. And if you have azimuthal modes, because these are spinning systems, they're also over the same time scales. So you can see, even when there's no turbulence in here. There are these acoustics and fluid mechanics can couple, and then if you look at the flame response time scales, maybe Tim or somebody may have talked about it, that's also the same time scale. So you can have acoustic vortex heat release interactions without turbulence and can lead to instability, and turbulence can combine with these time scales and produce new types of interactions. So it's not just the turbulence that is playing a role, it's heat release, flame, and combustion and acoustics all play countermanding roles about the system. Okay, I'm going to skip through some slides. These are there for so other point of mixing, you have I said fuel air mixing is important, and I said we can use premixing systems for gas turbines for power generation. Well, if you really think about it, there is perfect mixing requires molecular mixing, right? If you're thinking about mixing something, by definition the only way anything is perfectly mixed is at the molecular scales. So if you're mixing heavy liquids with air, it's never going to mix. You're going to have blobs of liquid floating around. If you vaporize it and get a lot of fuel vaporized and mix it with a lot of air, you're creating a big bomb essentially. And you have to mix it very well. That means you have to mix it, churn it. How do you mix it? You churn it up. That means you're creating turbulence in that mixing zone. Then you stick that into a combustor and you say, well, that flow is just coming in with like premixed. But it's not coming as premixed. It's coming as turbulent premixed already. And that turbulence is your creation. You have no clue what it is. Alternately, what you do is you premix, you put it in a tank and wait for a long time, and then assume everything is turbulence has died, and then you bring that in and assume there is no premix. But that is dangerous. You're creating a big bomb. So typically, and if you are a gas turbine, you have a building this big, and the gas turbine is sitting here. The premixer is only based on the space and size, limited in size. So there is nothing like a perfectly premixed system. Although in the lab you can create one because you're working on a small flame tube, but real systems are not perfectly premixed. So what you have there is that you have equivalence ratio variations in premixed systems, and that means that if you're running very lean, locally you can have the equivalence ratio below the flammability limit. It can blow out. You will never know what happened because it's nothing to do with the engine. Everything is fine. It's how you mixed it. So that becomes a problem. On the other hand, the non-premixed systems are also partially premixed because what happens is you mix after the evaporation, so there will be regions of fuel air mixing where it is already premixed locally. So you have local premixing occurring in liquid fuel systems. You have equivalence ratio variation in premixed systems. So the answer is everything is partially premixed. And if you look at the literature, it's only recently people even talk about partially premixed. Nobody talks about partially premixed because nobody knows how to do with that, because if you are looking at it from a modeling perspective, the model must work for both. The same model should handle premix and non-premix systems, and those of you who have done modeling should realize sometimes there are premix models that don't work for non-premix, and non-premix models never work for premix. So nobody can do the real system by definition, so that's the challenge. Can we deal with these systems with dealing with this partial premixing problem? I already mentioned some of this. The other point that I haven't really hit the picture yet is that these are complex geometries. In the cover page I showed you a bunch of complex geometries. Question is, can we deal with these complex geometries, or do we have to go to a very simple system? And the answer is you cannot. You have to deal with the complex geometries, because simple systems never exhibit half the things you're interested in. It never happened in the system. What happens is, like a lot of times in the lab, you have combustion instability or some physics occurring, and you learn a lot about it, but that never will happen in a real system, because real system is some other things going on. And you can never test the real system in a lab because it's too complicated. And those who know real engines, you can never put things in there to measure. You need laser diagnostics, you need to open it up, and thus becomes a tricky problem. So we have to deal with the system, and I'll talk about the excursion of the mean in a minute. The other point is that if you're going to work for a company, the company says, well, we want to run 500 simulations in 2 days. Many of you who went from IIT or for GE Bangalore, and they run fluent calculations, turn around everything every 4 days, they produce a result. And they run complex geometries and complex conditions, but they simplify everything else in order to get that answer. So a lot of times you get a lot of answers that may or may not have physically correct models, and so it is possible that each point in that database is wrong. So sometimes they say, well, we don't care about the actual answers, but we want the trend. Now sometimes you wonder whether the trend is correct if all the points are wrong, and that's never been answered to me yet, so but that is how industry does. Industry, if you go work in industry, they're running commercial codes, RANs, unsteady RANs, and they say, well, we're getting good results. Then if you ask them, what are you running? Oh, we're running the same case that they have built already. So then you say, well, why don't you change all that? Oh, no, we can't change everything because we'll have to test it again. So the testing has not gone away yet, even though they're starting to reduce it using modeling. So the question is, can we deal with these emission problems with unsteady RANs problems? And that's a difficult challenge. I've already talked about this, but what I wanted to point out also, I don't know if many of you have seen this, and I don't have time to go through. It's called the premix Borgy diagram. It is showing grid size over flame length over Karlovich numbers. It's kind of scales of turbulence. But what I wanted to point out is that DNS is sitting down here, laminar flamelets are sitting here. These are thin flame, I'll talk about that later, but this circle is where the laboratory flames sit. Those flames you have seen in Bunsen burners and swirl burners, they sit around here. The combustors, gas turbines are sitting, LM6000 is a GE combustor, this is a DOE, are sitting around where D1 is. As they go lean, they go here, they go this way. The lab flames are sitting here, the combustors, real rigs are sitting here. So you can see again, there's a lot of differences between where you are measuring things and learning and where they want to use them. And that's the challenge. So the question is, can we model these things without worrying about, when you cannot do an experiment on that? Another way to look at DNS and RANs and URNs, if the fluctuating black signal is the DNS field, the green one is what LES is trying to do. It filters out some scales and picks up some of it. URANs or something what I call VLES might pick up the red line. The steady state RANs will be that blue line. Because it's steady state, it doesn't have any of these fluctuations. If you average the signal, you might get the red line. The bottom line is that both the blue and the red has nothing to do with reality. You can see there is a lot of changes while the means don't show that. So even when you do LES and you look at time average results, you're really not learning much. For example, is a signal here from a combustion instability, and this is not a very good signal, but if you average it, the mean pressure is nearly zero, the pressure fluctuation is zero. So you see everything is great, but actually this fluctuation has blown the facility is blown up because the excursion from the mean is very large, and you don't have to have a lot. This is an experimental rig I'll show you later, which was controlled, but just going from here to there might be sufficient to blow up. So unsteady physics is more critical than the mean. So the average results, if you trust it, too bad. You know, you have to learn what is the peak to peak around the average that you have to know. If you don't have that information, you are very difficult to deal with it. Another problem, the word computational. That means we need computers. Well, what kind of computers? Maybe we have what we call a few petaflop machines. You know, this existing. Everybody claims there is a 20, 30, or I don't know, 100 petaflop machine, but those are what they call peak performance. All they're adding is 1 + 1 = 2 or something. You know, they're not doing real problems. Most peak systems you multiply by 0.1 or 0.01, and that's the performance you're going to get. The actual performance of the best codes might be production codes, maybe 5 to 10%, you know, of the peak. So if you think about, and this was some analysis done by IBM, NASA, and a few other people back many years ago, that if you want to really understand human vision, you need 100 teraflops of actual performance. You know, so that's already 10 petaflop machine. It doesn't exist yet. You know, and aerodynamics 1 petaflop, and here computational chemistry is what we call a zettaflop. You may have heard of exaflops now, but turbulent combustion, the guess is going to be beyond what they call a yottaflop. Which doesn't, it's just going to be faster than whatever. So the point is that we are not even in this picture. The machines that we have in your lab, my labs, are maybe we're getting 10 to 100 teraflops if you're lucky on hundreds of thousands of processors. But so the challenge is that computational modeling and computational combustion comes together. So I'm just going to go through a few quick things about how we want to do modeling. Well, you have to pick the problem, obviously, and if just somebody gives you a big problem, doesn't mean you can handle it. But the bigger question is, what are the questions you want to ask? That's the first thing. What do you want to know? And the why part is maybe some reason, but sometimes what is it that you want to extract? And given that and the geometry, you obviously have to define the grid. Everybody knows that. If you have to pick the scheme, I'm just giving you a flow chart, and I'm going to talk a little bit about boundary conditions and simulation things and post-processing. And the point of this flow chart is that you have sometimes you have no control over anything. You're given a geometry, you're given a grid, you're given a code, and say go run it. And you hit the button on whatever model it has, and it produces something. The question then becomes is that do you know where are the problems? Because the weakness, if everything is right, but one point is completely wrong, the sum total will be driven by the weak spot. And if the weak spot is something that you don't care about, that's good. But so that's what you will have to understand. So I'll just go through some. Many of you may know about these things. So typically grid generation, generating grids. Everybody talks about unstructured grids. Mainly it's because very easy. It's easy to generate. But is it good? It can do complex geometries, but can it do a real flame structure? To me the answer is no. It cannot do that because flames have structure. The grid clustering is done for a geometrical reason, so you end up becoming more biased, and I'll show you some grids. On the other hand, multi-block grid structured grids are very good for flames because you can put the grids where you want, but it is very expensive it's a user-heavy things that you have to work on. You can do adaptive mesh refinements and cut cell methods or immerse boundary methods where you can adapt the grid to the geometry, which is the best of both worlds, but then you have to deal with a lot of boundary condition issues that has its own problems. You can do overset and chimera grids where one grid is fixed and another grid moves around on it, like for rotorcrafts or rotor stator applications. but then you have to transfer information between different grids. So each of them has their good, bad, and the ugly, and I'm not going to have time to go through a lot of these things. I'm going to highlight quick points. I may be running out of time here. So here's a grid for a generated by a commercial of a jet in cross flow, and you can see that because of the geometry, grid clustered near the wall, but this is a jet. What you need is the grid to be refined here. So if you just use the grid blindly, you will get garbage. So you have to spend time refining the grid, and like for example, take that grid and the aspect ratio effects and put the grid properly to get the problem. But if you do that right, you can generate very complicated grids. Every geometry I showed you in the cover page was done using block structured grids. But it took us a while to generate grids. But we can control these grids. Like here, for example, is even more complicated grids. This is 3 sector of a CFM, and these are all structured grids. We are able to do complex geometries with structured grids, but it's not easy. Yeah. But on the other hand, you can trust the quality of the grid. You can see the quality of the grid around swirlers and regions, and that means when the fluid mechanics, because computational combustion is 90% is turbulence, that is you have to capture, which needs good grids, is more reasonable here, and you don't need to go to very large grids. That's another advantage, because you can run, for example, this was a 12 million cell grid. The same grid in unstructured might be close to 30 million grid points. Like for example, on the other hand, here's another combustor that looks similar to what I just showed with an unstructured grid, and notice that this is a flow that is coming out. You can see that the shear layer region right now is not well resolved. It's like a uniform, very arbitrary grid cells. So when you have a finite volume or finite element solvers with grids like this, you have numerical accuracy problems. So the solution here is that you have to put more and more and more grid to get fine things. So the cost can be going up. So unstructureds are easy to generate, but you have to be careful about where you put it. And if you increase the grid, it can become costly. Structures takes longer to prepare, but you can use coarser grids and can get a better. So which one do you pick? Sometimes, like I said, you're given something, so you don't have any choice. Other option is what I call an adaptive level set method, where the grid is irrelevant. You don't care about the grid. You put the geometry on a uniform grid, and you adapt the grid on the surface locally, and resolve the local structure. So grid generation is trivial. It doesn't exist. You just draw a line and you put the geometry on it. But then you have to be able to recover the viscous regions around that and get accurate structures. This is a technology we've been working on for recently, but we need to have accuracy to resolve this in combustion systems. But if you do that, you can do quite complicated problems, like this is a jet in cross flow. This is a cylinder moving in a flow creating a detonation. This is as opposed to what most people do, where cylinder is just sitting and the flow goes past it. Here the cylinder is actually moving and moving up and down. So it's a circular geometry on a square grid, but the circle is being recovered by this adaptive mesh refinement technique. So there are advantages of doing this kind of approaches, but there are problems too. I mean, that's the idea. For example, you have a grid that jumps from one grid to another grid. Looks okay, what's the big deal? AMR does that, all that. You can generate the grid, you can transfer the information. Well, what about turbulence then? You have finer cells here, right? So you have small scales. You go to a coarse grid, the small scales must go away. What do? Just get rid of it? Okay, that's fine. What happens if the flow is coming from here to there? Now you have large scales coming into small scales. It wants to generate small scales. Where is it going to get that information from? So these things are to also be understood, because, like I said, turbulence is everywhere. So for example, we have looked at some of this. So here's an example of isotropic turbulence this is the same grid. You can see it is perfectly no effect. That is going from a fine grid to a coarse grid. It has lost the small scales. It has the large scales. This is a coarse grid picture by itself. And this is the opposite, where your turbulence is going from coarse grid to fine grid. If you look at this like a noisy structure, you might say, well, all of them look great. Is that true? And the answer is yes and no. You have to be careful because you now have to look at the spectrums, the turbulent spectrum. Remember, we are talking about inertial range spectrums. So if you are staying in the inertial range, you want to look at these things. It turns out that if you go from fine to coarse, it is easier to deal with the transfer because the small scales are dissipating. So we can transfer the dissipation to the coarse grid. When you have coarse to fine, it has a coarse spectrum is correct up to the filter, but the high frequencies have more energy. So it is more noisier at the small scales because it is not physical. You're creating artificial turbulence in order to go from coarse to fine. So in other words, in this picture is okay, is more accurate. Going from here to here, you have created some small scale structures right at the interface which are unphysical. But it turns out that turbulence has a natural tendency to take care of itself, so it recovers a little bit later. So it actually recovers further downstream, and the turbulence recovers back to the fine scale. But then on the other hand, at the interface there's an error, and you have to be careful about that error because if a flame goes through that and it's hitting the turbulence right there, you are going to produce garbage. So the solution is make sure the flame doesn't go there. You refine the grid. You have to rearrange the grid, and that's where the adaptive nature comes in. Then the accuracy and physics becomes a issue problem. Some of the slides I've given you is more detailed. I will not go through that. You can download and look at it. Then the schemes that you are using. How much accurate do we need? Well, typically order fourth schemes are considered optimal. We need like an order fourth scheme to have reasonable application, but second order schemes are reasonable to work with. The problem is complex geometry is very difficult to get more than second orders. But the question is, are you really second order? If somebody says you're a second order scheme, I'll say prove it to me. And 90% of the codes are basically barely first order. Many of them are zeroth order. When I say that zeroth order means that essentially there's a lot of dissipation that is affecting the problem, and I'll show you some examples. And it's very difficult to quantify these things on real systems. The other aspects, and these are questions that I'm just leaving you with it. In geometry, a lot of people use explicit dissipation. What do you call artificial dissipation? Well, the word artificial means it's artificial, so why do you want to use it? Don't use it, but then the question is, if you can't use it, you need something, what can you do? Well, maybe you need a dissipative algorithm. At least you know the dissipation of the algorithm and use the algorithm as the artificial dissipation itself, rather than put something in to wipe out something in the hope that it doesn't do any effect. So, and then the boundary conditions, which I'll talk about that a little bit later. So there are many schemes out there, and I'm not really going into it. Another aspect, low Mach number versus compressible flows. Most people here, or most commercial codes, are what you may call pressure-based solvers. They are running what we call low Mach number codes. They are basically are incompressible flows, right? I mean, with heat release. They are the compressible looking equations, but they don't have acoustics. The acoustics have been removed. So the time scales for that is the convective time scale, so it can run faster. But then combustion makes noise. Everybody knows that. So is that noise important? Well, everybody says it's only important if you have instability. But turbulent combustion is always unstable. So by definition, the frequencies I showed you are at the same time scales. So in theory, acoustics is in combustion all the time. So when you do low Mach number problems, some of the turbulent physics may be lost. You may not see it and may not know about it, but then typically it's used for low speed laboratory flames. When you're doing high pressure combustion systems like gas turbines, combustion instability, supersonic combustion, you have to go to compressible flows. And obviously all supercritical systems are compressible. So practically, if you're working on lab flames, you can do low Mach number. If you're using real systems, you have to go to compressible. I mean, there is really no solution, alternate solution to that, because this is basically what I mentioned. because and I don't know if anybody knows, I written in low Mach number code. I'll show you an equation in a minute, but you have the pressure is a kinematic pressure. It is the equation of state is not actually playing a role in the incompressible equations. So when you have heat release, temperature goes up, density fluctuates, pressure will fluctuate, right? But pressure cannot fluctuate in the low Mach number regime because it will spread. It's an elliptical solver. That fluctuation will fill the entire domain. So the low Mach number codes have to kill that oscillation. So in some sense they are wiping out the physics of the turbulent flame interaction in order to make the code work, otherwise the code will not converge. So that's the fundamental problem. While this is not, and obviously that's why pressure solvers have convergence issues. Many times these pressure solvers don't converge. They iterate 5 times and move on. They don't really converge. So on the other hand, compressible problems obviously have other advantages. So this is what I was saying about the low Mach number. You do an expansion on Mach number, and the pressure, you have the low baseline pressure which satisfies the equation of state, but the momentum equation contains the first order Mach number pressure. It doesn't contain the acoustic pressure. So even though the equations look like the compressible equations, they are not the compressible equations. The main pressure depends on the dilatation, and obviously this has to be satisfied. And that's where the problem comes in. So I'm not going to get into these aspects that much. Compressible codes, we use a lot of, most of the results I'm going to show is based on my codes. It's called Leslie large eddy simulation with linear eddy, and I'll discuss that tomorrow. It has lots of algorithms. We use McCormick type predictor corrector with none of them are explicit dissipation, but some have inbuilt dissipation, like muscle Riemann solvers. They are third order accurate. We have some compact schemes, but for these we have to have explicit filtering to get higher order filtering to keep it stable. We also have finite difference schemes, but we don't use it for more practical purposes because many of them have limitations. And if you have read CFD papers, you can find out, but every scheme has its strengths and weaknesses. Some are fast, some are easy, some have problems. They cannot, for example, compact schemes can only do smooth flows, needs Cartesian grids. You cannot have curvilinear grids. Muscle and McCormick can deal convincing grids, but this has lots of knobs. So the point is that there is no one solution for every problem. What you can hope for is to build a hybrid solver where you have solvers, algorithms based on the kind of physics you are trying to solve, and typically we have hybrid solvers that does central type schemes in regions where there are no shocks or discontinuities, and switches to locally to muscle or Vino type schemes when there are shocks or sharp discontinuities. So again, these are CFD techniques problems, but you can then look at actually the accuracies, and you can see that if you do a linear Euler test, isentropic vortex test, and passive scalar test, you can actually prove that when I say something is 8th order or 6th order, you are getting 6th order accuracy. But these are always with uniform grids. So it is always worthwhile to then go and test it with slightly variable grids to see how bad the accuracy starts to vary if you have slightly stretched grids. Still Cartesian, like delta x is different to delta y to delta z, and you'll see that suddenly the accuracy drops. Some schemes will become very bad if the grid is not uniform in all 3 directions. And some of them will say, well, I'm only, instead of 5th order, I'm now 4.2. So that's good, because so you have to know where you stand in order to use these kind of grids. So typically what we use is 2nd to 4th order schemes, and we use 2nd to 4th order in time. That's the typical baseline of what we use, and I wanted to show you some results here. This is a 2D vortex, and it's just spinning around, and you can see it starts off with an initial solution like this, and after 10 rotations, a 2nd order scheme has become like that. By the time it reached 40 cycles, it's gone. The vortex has completely disappeared. You If you go to a third order, it gets a little better. If you go to a fourth order, it gets better. If it goes to compact, it looks almost perfect. Sixth, you know. So you would say, hey, I want to use compact, but it's good only for this problem. You know, next problem you use, it'll go berserk. You know, so the point is that you need to at least you know what it is doing. So for example, in this one, I would say, and if we see, and like I said, we use a hybrid of these two because this works in many regions more accurately. For example, here is a case of a hybrid second order, fourth order central scheme with a supersonic sonic jet into a Mach 1.6 cross flow. So we're using the muscle schemes to capture the shocks and using the fourth order schemes to capture the boundary layer and the shock turbulence. And you can see the Mach curve forming. This is non-reacting, this is pure turbulence. This side we are showing URMS, that is experimental plot, and the right hand side of this side is the LES prediction. So there's a paper in there published where, but what I'm saying is that with hybrid methods you can try to get the best of both. You'll never get the best of both, but it's better than either one and better than some schemes that look much more accurate in other regions. Here's another example of a higher order finite difference. Now, a lot of DNS codes are finite difference because you are in a box. If you're doing a box problem, finite difference are very good. They give you very good accuracy. So here's a hybrid second order muscle. This is a shock vortex interaction case, and this is a compact muscle finite volume. These are finite volume schemes, and this is a finite difference scheme, a very high order. You can see that some of the basic features are captured by dissipative solvers, but some of the scales here are oscillating while this is much more smoother. Now I could increase the resolution here and get better answer because this is way cheaper than that cost wise. So again, you know, it's not that everybody is at the same price. That might cost 4 times more for the same grid. So I could double the grid here and may cost the same amount and might get a better answer. But the question you have to ask yourself is that do you want to do that? You know, do we need to do that all the time or not? Here's another example of a shock interacting with a solid wall and reflecting. This is a pure second order scheme, and that's a 6th order scheme with a 5th order Vino. And you can see that the shocks are relatively captured correctly with the second order. What's missing is that structural features, the slip line, which is well captured in that region. Now slip lines are important. You're probably not going to get it here, you know, but if you're only interested in the shock reflection and pressure rise, this is good enough, you know. Again, these are kind of the evaluations you have to do. Here's another one which is an oblique shock interacting with a mixing layer. Again, this is the baseline code. If we are using the same grid, remember that the cost is going up as we go down because the scheme is more expensive. You can see that this one captures the interface, but this one also has most of the features. Yeah.
So the model of the scheme which you are advertising, that holds in very strong condition.
Strong condition, right? That's what.
So when you are trying to apply them for these cases, is there at least like a lower limit where that such a minimum order will be enforced even in a very
Yeah, most schemes, and there was we have a discussion. Most schemes essentially, when you use the hybrid, are barely second order. I mean, yeah, all schemes drop to second order accuracy. You can prove it that in the most schemes stay second order. It's just that the higher order have less artificial dissipation when the schemes when there are no shocks or turning on, when the grids are uniform. So typically the bottom line is that these things have less artificial higher order dissipation, higher order schemes when in these test problems, but in complex problems, once you have this shock type problem, they are all second order. And the shock is typically first order, you know. So the question you always have to ask is second order schemes. If it is truly second order, they may stay as bad. It'll never get worse. Let's put it that way. You know, the higher order schemes look good in a lot of problems, and in a lot of places it'll do a better job. But when it comes down to a real complicated problem, it may not even work. That's the other point. There's, you know, the complexity of higher order schemes. We have big stencils and complex geometry, the code will start crashing, you know. So you'll end up doing what you end up people doing is that you go to second order near the walls, go sixth order there, then you're mixing it all up, you know. So there becomes a challenge. I mean, if you have a good algorithm, maybe you can do it, but typically we don't use these problems. I mean, we use it for these nice little problems, but we can use the hybrid second, fourth order muscle for every problem. So if you learn the limits of the problem, you can work with that, you know. So here is another example of a flame. This is now a DNS of a flame experiment. DNS, this flame doesn't exist. It's an experiment. DNS flame it was done with 52 million grid points. It had 17 million grid points in the LES, and we went down to coarse grids, and we are running 13 species, 50 reactions in both the model. There's a subgrid model in there. I won't get into that, but again, here that's the DNS result, and this is a flame surface, instantaneous flame surface. This is a sixth order scheme. This is a second order scheme. Again, you know, I mean, overall features come out overall reasonable, but if you look carefully, there are differences. For example, here, when the grid is coarser than 3 times the DNS, what I'm showing here is the black line is the white line is the progress variable from the DNS, and the solid line is the LES, and the dash line, the whites are DNS and the blacks are LES. So this is showing the width of the shear layer. This is the time average picture. Remember, this is instantaneous. This is the average picture. So you can see that this picture has nothing to do with that, you know, even though it is the result of that. But in an average sense, you can see that the compact scheme is doing a good job when the grid is only 3 times coarser. So you say, hey, compact is looking good, because the second order scheme is not predicting the flame length. You're getting the shear layer okay, but not predicting the flame length. If you go to 5 times coarser grid, you can see that the second order scheme hasn't gone that bad. It's still as bad as this one, you know. But the compact scheme has gone the opposite. It's gone bad. You know, now it's over predicting the flame, you know. So again, some of the schemes, higher order schemes are good if the grids are good and the grids are fine, and you have to balance that with the cost of the problem, because compact schemes are obviously more expensive than second order schemes. I got a few more minutes to do this DNS. So boundary conditions. It is pretty much the ball game. My code maybe has 10 million lines of code, but maybe 5 million lines is boundary conditions. So one wrong boundary condition is the end of the game. So it's and especially with compressible flows, and I'll show you some examples. And it is important to understand the inflow outflow. What's coming in, what's going out. Walls have their own problems, but inflow outflow is a big problem, and maybe many of you have studied it. And even supersonic problems are problematic because you have a supersonic flow on a wall, and if it's a viscous wall, it's a no slip boundary condition, so there is a subsonic boundary layer near the wall. So you have a mixed boundary condition. It's not all supersonic. You have a subsonic outflow and a supersonic outflow. So typically is well known in many books called the characteristic based Navier-Stokes solver. So we actually have a Navier-Stokes equation written in characteristic form, and we have to prescribe what's coming in and what's going out. And I'll show you some, these are just details, you may want to look at it. And there are many ways of looking at it, but so when you have subsonic inflow, one wave is leaving the domain, the U minus C, and let me show you these are Navier-Stokes equations written in, these are all in books, I guess you can get it. But these are the characteristic wave speeds. So you have one wave that is U1, velocity minus speed of sound, and one is plus, and the others are velocity. So the subsonic inflow U minus C is going back. That means it's leaving the domain into the inflow. So one variable cannot be prescribed. It has to come from inside. The question is, how do you prescribe it, and what do you prescribe it? And if it is outflow, then one boundary condition is coming from outside. That means you need to know what's going on in the lab. You know, that actually is a very serious problem. You know, I'll give you some examples in our lab that happened. So I'll skip through some of these typical classical issues, and then when you do these problems, you realize that you can have the inflow can be reflecting, because acoustics can go out, come back in, or non-reflecting or partially reflecting. You can have a whole variation of that. And if you're trying to model a lab facility, you don't know what's coming in. You ask the experimental guy, he says, well, I turned it on, it's choked there, something, I'm not measuring what's coming in. But this is the mass flow rate. So they may give you a mass flow rate, but typically what you need is pressure, density, temperature, and the velocities. How are you going to get it out of that? The characteristic BCs can give you that, but you have to then decide if you have a constant mass flow rate, what variable mass flow rate is, let's say area is fixed. If you say m dot is rho density times velocity times area is fixed. If mass flow rate is fixed, means density and velocity has to change to keep the mass flow rate fixed. So now you have two things varying. So how do you vary that? If density varies and temperature is fixed, pressure is going to vary. So it's all tied together. It's not simple as saying, okay, I'm going to set something and go through that. So here's an example of a non-reflecting inflow. There's an acoustic wave going in and we are killing it. Nothing is allowed to come back. The flow doesn't reflect. Now in this one, I'm completely reflecting it. I want to reflect it perfectly and it comes back perfectly. Using the same characteristic boundary condition, there is a knob you can twist back and forth to get between those, and you can vary it in between. Sometimes you don't know what your inflow is, and the experimental guys will never tell you what the inflow is, and all the results you're predicting is controlled by that inflow. So you may have to worry about this more than your code and your algorithm and your grid, and we have had to spend a lot of time on that. And let's give you another example. Here's another similar example, but actually with some example of a pressure wave. Same wave is going in. So velocity is going that way, the wave is going the opposite and it's hitting the inflow. This is a classical test problem. If you write a code, you can use this for testing. So in this one, it's perfectly non-reflecting. So it starts off at t equals 0 and it slowly goes in. After a while, nothing comes back out. It's flat. Pressure has disappeared. Everything is dead. That means the inflow is not affecting the system at all. This is semi-reflecting, so we put some tuned it, so some of it is coming back. This is reflecting, and the difference is that the top picture was with a delta P of only 1000 Pascal, very little pressure. So it looks nice. If you now make it 30,000 Pascal, that means a little bit high pressure drop, the solution becomes much more different. So small changes have big amplification of just boundary conditions. Now remember, this boundary conditions is what driving everything down, and this is nothing to do with combustion. Now this is at Mach 0.01. Okay, what happens if you go to Mach 0.8? Same problem. Things become much more crazier. You start getting all these wiggles because these reflections are each reflection is reflecting back. Each reflecting is creating its own reflection and own reflection and own reflection. So and each one is reflecting back, so you get banging noise, what we call banging noise. And as long as it doesn't grow, you may be able to live with it, But again, it also there's a combination of problems. So that's inflow problems. Outflow has its own problems. You have let's say you have a isentropic vortex just going through. You just want to have a vortex leave the domain without creating any disturbance, causing any trouble. And so we can have here's a vortex just leaving it. These are wall regions, very little, that's nothing going on. Non-reflecting, it goes out, you can see it's coming out. Semi-reflecting, this is at very low reference velocity, very weak vortex. If you just say, oh, I'm just letting it go out, let me just extrapolate. Everybody extrapolates, and most codes extrapolate. You can see the vortex already changed before it left. Now, if this was burning, good luck. You're going to get a huge instability out there. So if you it's pure supersonic, which means that everything is extrapolated, that will not work. Now, if I increase it to slightly higher strength, supersonic goes berserk. While the reflecting ones still work, or the semi-reflecting ones work. If you go to compressible, sometimes it's that was subsonic, that was low speed, right? Now as you go to higher speeds and the flow is going really fast and the vortex is weak, extrapolation might actually work. The vortex can go away too fast before the flow realizes it's gone. So So again, so you would say that I'm running, so if you know what the problem is and what the flow is, then you start pushing forward to that problem. So so inflow and outflow boundary conditions, and these are only axial problems. So if you had a flow going like this and you wave going that way, it can happen in complex geometry, then you have to deal with three-dimensional boundary conditions. So typically in codes like ours, the boundary conditions are written in full 3D. It's a complete solver in itself in characteristic form. And if it is burning, you have to carry species, reaction flames. So typically you don't want a flame to go out of the boundary. You'll have trouble. So you have to keep the boundary far enough. Actually, in the experiments also, the good thing is that the flames don't go out of the boundary because it'll burn in the outflow, right? So they are also compact. A lot of combustors, practical combustors, are very nice because of swirl. The flames are very compact. The flames don't go out. Everything is burned very quickly, and I'll show you some results in the next couple of days. What goes out is all products, but you still have to be careful about what's going on. If it's a big structure of big blob of products going out, you might create instability that will feed back, and then you might get a result that you may say, hey, this looks like real physics, but it's not physics. It's all boundary conditions. So you have to separate the physics from the boundary conditions, and it's always very interesting because I actually there was an experiment done at Georgia Tech by, I won't name who, but they did lean blowout on a liquid fuel spray combustor, liquid fuel kerosene spray combustor, and in the original combustor it was just this much. This piece was not there. And when we were doing, then they gave up on they finished the experiment, so I decided to do some data acquisition to do modeling. And when we started measuring the spray droplet velocities, we found that the spray was very cockeyed. Didn't make sense, and the flow, the actual velocity around the center line was negative. So we decided to figure out what's coming out. So we didn't measure anything, we just measured the exit. This facility was sitting in the lab, in the open lab. It turned out that the flow was coming in the core and going out around the sides. So the flow was going out, but it was also sucking in the lab air. So from a characteristic boundary condition point of view, now you have an inflow and an outflow at the outflow. So it's a mathematically ill-defined problem. That means you can go outside of the boundary condition, throw something in front of the back, and we did that. We started blowing jets of air right at the exit like this, and it would change the flame. So the outflow was controlling the inflow. So the only way to eliminate that was to put this convergence so that the flow would accelerate and kill the reverse flow in the center line. So rule number one in the outflow in compressible flows is that if the outflow is negative, don't even start doing any work. Tell the experimental guy to go back and redo the experiment, because that is a mathematically ill-defined problem. So that's why I was showing you here a little while ago. I'm going to go back to that grid, because the reason that grid looks so complicated. I'll stop right now. Like not this one. This one, we're actually simulating this experimental rig. The combustor is this. That's the combustor. This is the inflow. That's the inflow. So you would say, I just want to do from here to here. You couldn't do it because nobody knows what's inflow and what's outflow. And the way the experiment guys are doing it, they're putting this chamber out there. This is the entire test facility. So we have to model all the way from here to the inlet, even though all I'm interested in is in that little spot around that region. The only region, the entire combustion is occurring in just that one less than 4 centimeters long, and this is about 1.5 meters. So we have to waste a lot of computational power modeling the rigs, mainly because the combustion is occurring right here. This is the spray, this is the annular flow, it's occurring here, and this piece is just that little spot. But because we don't know what's coming in and going out, we have to do this full rig. Because at this location, we hope everything is okay. If this is negative, you're back to square one again. At least the inflow is okay because usually you have pipes and choked flow meters, so your flow is coming in. But a lot of times, in the experiments the outflow is not well defined. So inflow is problematic from a setup point of view, outflow is problematic from a reality point of view, especially if you're trying to match some experimental data. So we will, as we go further, I'll show you some examples of what happens if you miss some of these things. But I think I'm done for the first lecture. I think that is all I had. We'll continue. I guess we have a 10-minute break, or what is it, half an hour break, and then we'll continue with lecture 2, which is also related to modeling. Any questions? Yeah, sorry. Yeah, any questions? Right. That's methane. And that chemistry is available on the web. You can download it. It was done at Sandia National Labs, and it's a 13 species, 50 reactions. You can download it in the Chemkin format. Yeah. That's even worse. I didn't even mention that yet. But the entrainment boundary is what we call a mixed boundary. That's an inflow-outflow boundary. So you have to. It's just like the supersonic boundary I was saying. You have to use characteristic boundary conditions. And when you switch from a flow this way, you switch to an inflow, and when you go that way, you have to go an outflow. So if you just extrapolate, it becomes wave pressures will come back. So good solution, if you can, is to take the entrainment boundary far and far out, so that it becomes less and less effective. But if you are doing a free jet, you have to be quite far off. The jet is like that; you have to be far off. Otherwise, the jet spreading will get completely messed up. Yeah, entrainment boundary is even worse. I didn't talk about that. Good in the combustors, we have walls. So that saves us from that problem. But free jets have a bigger problem. Yes.
So when you go from coarse to fine and adaptive mesh refinement, is the source of the artificial turbulence only at the transition, or even the refined cells give rise to Fourier's perspective?
No, because you're solving the solver there. So it's just in the transition is where you have to transfer the information. Here you have a solver. If it's second order, it's second order there, it's second order there. The transition typically we have to interpolate or extrapolate. So that interpolation typically I didn't mention is actually higher order than each solver, but just interpolating and creating the cells, that the energy content is where the problem is. So going from fine to coarse, information going like that is easier than from coarse to fine, but the coarse to fine, the small turbulence you get dissipates quickly. So if that's what I was saying, that if the flame was sitting right there, you have a trouble. If your flame is sitting here, it doesn't matter. It'll recover itself. Yeah.
As a follow-up on this question, so if we are having a turbulent flow and initially we are going from coarse to fine, how do we actually create the small scales which are required in the you're basically creating an interpolation like it's the AMR type schemes. You just take the volume fluxes and create an average of that. So by doing that, you're creating small scales. But it turns out that the fine to coarse, coarse to fine, that interpolation creates artificial noise. That's about the only thing, But there are different ways, just like adaptive mesh refinement people are doing. You can use the same thing. The interpolation scheme which is to be employed by going from coarse to fine, is it scheme dependent or?
No, it is based on, well, I forgot to mention, all these things are kind of assumes the grids are uniform. Okay, so it's not scheme dependent, it's more grid dependent. It's more grid dependent, and typically you try to use a higher order method, because you want to do, if the base scheme is a second order, you want to do a fourth order adaptation, if you can, but if you cannot, then you have to live with it. Yeah, no, he was talking.
Yeah. In general, we expect that the energy is being cascaded from the larger scales to the smaller scales, which may not be true when you have like droplets of the size of your very small grids. And especially it becomes more complicated when you have Lagrangian partial tracking, where you have parcels, not actual droplets.
Right.
So how do we account that in energy produced in smaller scales from a
Yeah,
particle?
I will talk about later, but you can, yes, I mean, that's true, because when you do Lagrangian particles, we assume they are point particles,
Yes.
and by definition, they're considered smaller than the Kolmogorov scale. That's the only way you can use it. So what you do is that when you are computing the drag for the particles, there is a difference between the gas velocity and the particle velocity. You have to add a fluctuation to it, and the fluctuation is based on the subgrid kinetic energy that you have to track, and I'll show that later on. But it is an approximation, because the point particles, by definition, there's nothing like a point particle. And I will also show you that if you carry more than 8 particles to a parcel, the error will go up. I mean, there's a limit to how many particles per parcel you can carry, And so the subgrid model has to account for the fact that the particle drag is affecting the turbulence. And so the feedback is at the drag law, in the Stokes drag law. That's about the only thing we can do at this point. It is a stochastic, it's called the stochastic method for drag. I'll talk about that probably in the last class, last lecture.
Thank you.
Over here.
Yeah, what is the general or typical this computational time for all this analysis you do under the mesh size, grid size?
Well, I mean, depends on the problem, but sometimes we are running for a month, on 1,000 processors. But this is LES, so it's not like DNS, so we are able to turn around many of these simulations in a week. And we are talking about running with 10 million grid points, with 5 million parcels, with 30 species, but we are also running on 3,000 processors,
Thank you.
Sir, you have shown a DNS where a finite difference scheme has been used, and you told it's for a box structure, and it was compressible flow. So can it be used if the geometry is not so even, that finite difference scheme for compressible flow?
Well, the answer is yes and no, because the finite difference accuracy is much more achievable when the grids are Cartesian and uniform, but not uniform. It is not body conforming. I mean, in curved grids, as long as it's Cartesian, you can still use it. In stretching, slight small stretching, even body conforming grids, you cannot have more than 5% stretching. But if you have a Cartesian grid and it's weak stretching, you can do finite difference. But complex geometries, when the curves become, then you have to, it becomes very difficult and has a lot of errors. It will become unstable. So most DNS codes, like from Sandia, Jackie Chen, and everybody else, they use finite difference because they can maintain 8th order accuracy, but the grid is basically box. It's a rectangular, not a square box. Can be different grids in each direction, but not curved. When you have curves, you have finite volume is much more powerful for that type of complex geometries. So if you have a pipe, a Cartesian grid will not do a good job. Cut cell method with Cartesian will do a better job, but Cartesian grid will have a lot of errors.
So for the vortex case you showed, where you compared the second order and the fourth order, we actually did it in Fluent, and noise was very much.
Well, of course.
It was very large. I mean, and we.
But sometimes it is the numerical. The scheme has nothing to do with what you're getting. It's the algorithm has been artificially dissipated, or there's something going on in there. Because if you've done Fluent, the Fluent will never crash.
Yeah.
Right? My code crashes the moment you start it. It's designed to crash.
And the fourth order scheme actually captures that. I mean.
Fourth order we can get that, and even second order is not bad, with this. But what I was getting at was that these schemes have no artificial dissipation. It's inbuilt into the algorithm, but we're not putting anything else, and there is no option to put it either. People try to put in an option, they're not allowed to. So. But the idea of the code that is robust is actually very bad in my view, because that does not allow you to learn from your mistakes. Because the code always runs, you think you have done everything okay. I have seen people showing me
atmospheric flow with density 7.8 kilograms per second. I said, doesn't look right. Why is it 7? They said the code provided that. I said, but it's atmospheric. What is the density of atmospheric air? Then it's like, oh, what happened? The code ran. Code produced an answer. The other thing, interesting thing about fluent type codes are that you take a turbulent flow and keep refining the grid. Like say you put isotropic box at 32 cube, it produces nothing. It's all smooth, no action. You start refining the grid, it may not allow you to do it, but let's say you went to 512 cube, you'll suddenly find it produces turbulence. And it's basically the numerical noise is starting to trigger noise. It looks like turbulence, acts like turbulence, but it's not turbulence. So typically, when you look at commercial codes, you want to see, can it produce isotropic turbulence, a decaying isotropic turbulence? After all, it's very easy. It's a box, uniform box. You take the energy spectrum and just put some noise and let it recover the Kolmogorov spectrum, and you'll find that most codes, not just commercial codes, I shouldn't be blaming Fluent only, but most codes, unless they can produce it, it is not doing turbulence. So you have to prove the code can do turbulence, and that's where these schemes come in play. The accuracy of the schemes come in.
My question was around that. I mean, okay, when you do a vortex case, you see a lot of noise.
Right.
Okay. So, but when they do validations, those simple cases don't
do anything. Yeah. All it tells you is the code algorithm is right, coded correct. That's about all it tells you. So that's what I'm saying. The next step is to show isotropic turbulence, show that you can, and I'll show you some results in the next set of lectures. You want to predict. That's why I said even though turbulence is unknown, the physics of turbulence is reasonably the Kolmogorov's hypothesis nobody has proven wrong. Even recently somebody ran a DNS of 8,000 cube, and they still produce the same type of spectrum. So the question is, can we produce realistic turbulence quantities from a calculation with these kind of schemes? Then you can start trusting that it can do turbulence. So that's the next step. All this tells you there's no bug in the code. It is producing the same. Like for example, the shock strength here can be hand calculated, so you can see whether that's coming out. But this doesn't say anything about real problems, and that's the other point. This also only tells you that okay, this guy is still good in this simple problem, may not be very good, but if I take this and do a gas turbine, it'll never work. The code will crash. It cannot be done. So. But these two problems can do that. Somebody, no, that's fine. I can answer questions. Yeah, I'm fine. It's important to answer when they're still remembering. I may not remember either.
You initially mentioned that unsteady combustion need not be unstable combustion. So when you are looking at a flame and you see turbulent structures and unsteadiness, how do you distinguish that whether this flame is unsteady? Okay, because it is turbulent, but how do you know that?
No, see, unsteady, there are two parts. Unsteady means it's just unsteady. Take different snapshots, because we are doing time steps of 10 to minus 7, or if you look at different snapshots, you will see statistically the flame doesn't look the same. If you average it and you still see some unsteady features, those are the large scale unsteadiness. But if you average all of them and you get like a smooth profile, that's the steady state. So the unsteady part is both large scales and small scales. The instability part is different. That's when the oscillations become very large, and they need not be turbulent, because the combustion instability is low frequency. They usually trigger the large structures. But the turbulence can be unstable, fluctuating at small scales and large scales. So those flame-like structures that they showed, every snapshot will give you a different picture. And if you refine the grid, you'll get finer scales. But it is not growing in time. So unstable means it is fluctuating in time, but there is peak to peak is small. Unstable, unsteady, and unstable means that fluctuation is growing, and that's instability.
Mean like you have to see the pressure signal.
Yeah, in fact we have pressure, velocity, and vorticity trace data points, and we take spectrums. you have to store it in time. Yeah, data processing is a big issue, and I'll talk about that in the next lecture. Here's some.
Just 1 second, speak to the mic. It's all being recorded, so we want everyone to benefit from this Q&A session.
So for the reflective and non-reflective boundary conditions, for practical applications, is there any way beyond a certain Mach number you use better to go for reflective and beyond certain any Mach number or such number that beyond you can use a reflective or non-reflective?
Because I was mentioning most of these are compressible flows. In low Mach numbers have no boundary condition, they just extrapolate. Because they don't have the acoustics. So that U plus C and U minus C doesn't exist. So their systems don't allow you to, so if you have acoustics in a low Mach number type problem, then your boundary conditions cannot handle it, they won't even know. But if you're doing compressible, then the boundary conditions are determined by the actual, what you are trying to simulate, So that's, like I said, you can have a constant mass flow boundary condition where the velocity will float, you'll have to adjust, but you can have a constant velocity boundary condition where the mass flow will float. You can, so because of characteristic reasons, you have many options. And the point is that that's why I said you have to pick the problem and understand what you're trying to achieve. And if you're doing a system like this, then if the inflow if the experiment is a constant mass flow, then you have to deal with the mass flow. But then you have to be careful about what is your reflection coefficient. And there is no hard rule. You have to learn from practice,
Sir, in the pressure-based solver, you were saying that it doesn't use the gas, the equation of state.
It uses it, but it's separately. The momentum equation doesn't have that P0 term. You impose the dp/dt term by the dilatation effect. So the thermodynamics is included, but not in the momentum. The pressure that appears in the momentum is the first order pressure. So that is why it's a pressure solver. The P1 is being solved as an elliptical solver, like a Poisson solver, which is why it runs faster, because the governing equations don't have speed of sound as their CFL criteria is not there. It is just delta x over u instead of delta x over u plus c. So it has larger time steps. But if it creates acoustics, you'll have problems. If you get fluctuations because of heat release, it actually has problems. So the pressure solver may not converge. But yeah, so that's the why it's not there. But the thermodynamics is balanced by the dilatation effect separately.
Sir, what about AUSM scheme?
Awesome, yeah, that's like row scheme, awesome scheme. Awesome plus is supposed to be a little better, but they're also very dissipative. It works for some problems. See, that's the whole good thing about these schemes. All schemes work for some problem perfectly, and the question is, then you take it to another problem, will it work the same way? And that's what you'll have to it might run, but might produce wrong answers. And that's where, if you know what it is wrong, that's good. If you don't know and you trust the scheme, it's bad. So we have awesome scheme in our code too, but we are not using it. We are using this hybrid muscle type schemes, mainly because we have experience with it.